the Q&A session, which follows the presentation. There is a survey after the presentation, and you will be asked to submit your email address, so please make sure to stay for the entire webinar. If you have any feedback and suggestions to improve this webinar series, or any suggestion for future webinar topics or guest speakers, please share it with us through the survey. Our guest speaker today is Mr. Nick Shrawder with PennDOT, and he will share PennDOT's experience with recent adoption and initiatives to advancing the state of practice for NDE of fabricated steel structures. So you can type your questions in the chat box, and Nick will answer your question after the presentation. So with that, I will pass it to Nick for his presentation. Nick?
Okay, can you hear me?
Yes.
All right, thank you, Hoda, for the opportunity to present here today. Thanks everybody for joining us. I really do enjoy these NDE webinar exchanges. It kind of gives us a glimpse here at PennDOT of what the other states are doing, and kind of we can build off of that. It's a nice sharing platform. So the presentation is mainly going to revolve around newly fabricated structural steel. My background is primarily in structural steel for NDE, but I did want to go through a little montage of some of the more interesting projects I dealt with for in-service infrastructure as well, focusing on steel. So I'll start with that. But first, here's a glimpse of PennDOT, our overall operation. We have more than 25,000 bridges, more than 40,000 miles of roadway that we maintain. So we're a pretty large operation. So there's a significant amount of new infrastructure built every year to try to replace our deteriorating bridges currently in service. So starting with that, our in-service infrastructure, 20th century infrastructure, right? So NDE for us is, and other states as well, I believe, is primarily used as a supplement to visual inspection. And this isn't going to be an all-inclusive application of how we use NDE for in-service infrastructure. But like I said, it's some of the more interesting projects that I got to deal with over the years. So we've applied on structures that endure impact damage, known issues with detailing or fatigue, and some of those more unique circumstances. So starting with impact damage, this was one of those structures where the bridge isn't too low. It was a garbage truck forgot to put its forks down when it was exiting the ramp or traveling down the road, and it smacked into the bridge, caused a significant amount of damage. So obviously the bridge was closed. Both the overpass and the underpass for traffic, it was closed. And the very next day we did an NDE investigation, applying your typical ultrasonic testing, mag particle testing, dye penetrant testing, looking at the critical areas to see if we could open the roadways back up. So the critical areas being those toes of welds in this case, where it's more prone to crack when it endures a large impact, such as a trash truck driving down the road with its forks up. So this one, it was the repair process. NDE was applied throughout the entire repair process. Obviously, the initial investigation to determine if any cracks were there and to mitigate those cracks. And then as it was heat straightened, NDE was applied throughout that process too, to see if any other cracks had developed through the process. So like I said, this was one of those interesting projects that I got to be involved with. And here's another one that was kind of same impact type damage. In this case, it was the very cranes that we used to build our bridges that caused the damage. It was being transported from one job site to the next, and it just so happened that somebody forgot to secure the boom, and the boom was bouncing around and it was traveling down the road, and it got latched onto the underside of the girder and caused obviously a great deal of damage. So in this case, NDE was obviously applied up front for the initial investigation to determine what needed to be done if traffic can be opened back up on the on the traffic traveling under the bridge. Obviously not on the bridge, but so but we also the engineering solution to this particular project was that they wanted to try to salvage the top flange. There was no apparent damage to the concrete, and this was a composite bridge deck. So they wanted to try to salvage the top flange. So that encompassed cutting out the damaged member and replacing it with new a new member. So, but it was all contingent on there being no cracks in the top flange. So once all the work was done, you can see here that the transverse stiffeners were pulled out of the welds that connect to that top flange. So every one of those locations and every one of the locations where web to flange fillet weld was performed needed to be thoroughly inspected to ensure that there was no cracking in the top flange. So they lucked out in this instance, and there was actually no cracking. So they were able to reuse that top flange. So, and then I think most states still have a significant number of pin and hanger assemblies and truss bridges that they use pins. So we routinely inspect those for any type of wiring damage. So we actually have now allowed, in some special provisions on maintenance contracts, the use of phased array ultrasonic testing to inspect these pins, which give you a little bit better view and permanent record for doing some type of condition monitoring. So, and fatigue cracking. So, like I said, NDE for in-service infrastructure is really used as a supplement to aid in the visual inspection process. So on some of the older structures where there's known fatigue issues and there's something that that kind of hints to the inspector it needs a little bit more thorough investigation, we will apply some type of NDE measure to help them understand if there is some type of fatigue cracking going on there, which would not be apparent to just looking at it, right? So in this case, I actually performed the NDE on this bridge, and you could not see the fatigue cracking without applying some type of NDE, and NDE actually aided in the decision making for this particular structure to ultimately program, remove, and replace. So for some of the fatigue cracking that we have, obviously a mitigation measure is to crack arrest holes. And normally crack arrest holes and perform some type of mag particle inspection to ensure that it was fully drilled out is reassuring enough. But there's certain cases where they're tight fit areas, you can't really get some type of mag yoke in there, or it's difficult to drill out. So we will apply that reassurance and also add in radiography of those codes to make sure that we caught the crack. We fully removed the crack. So, and this project here wasn't exactly ours. It was the Pennsylvania Turnpike, but it was very close to home. And I actually spent a day down on this project where trying to understand their approach to NDE of the structure once they found these weld-filled hole fractures. So this particular one, I put this in here because it's always a good idea when you get into those one-off circumstances, those one-off situations where it's not covered in any code, it's not covered in any type of specification. It's always good to make some type of demonstration block or some type of mock-up block to perform a test, a practice test to make sure that you can find what you're looking for. So there's nothing in the codes that would address these weld-filled holes currently. So that's exactly what they did on this project. And like I said, I spent a day down there just playing around with these blocks, and they made them pretty difficult to locate the weld-filled holes, to mimic those weld-filled holes. And they were actually qualifying inspectors to go on the bridge with these plates. If they couldn't find it in the test blocks, they weren't allowed to be on the bridge testing. So moving forward here, 21st century infrastructure. So this would be our new infrastructure, newly fabricated structural steel. Um, so PennDOT has a strategic plan in place right now that that includes digital delivery. So digital delivery kind of focuses on the 3D modeling, the open bridge design stuff, all that stuff, plan lists, drawings. But some of these new NDE practices kind of fit right into the scope of that pr- that uh that plan. These advanced NDE technologies are very digital in nature. It's very data driven. There's no paper component with it, or you can get away from the paper component. And we're getting more than what we used to. So currently, NDE for steel bridges, newly fabricated steel bridges, we follow the AASHTO AWS Bridge Welding Code. It addresses all the standard practices for NDE of welds, fillet welds, full penetration welds, partial penetration welds. But there really hasn't been a huge change in the NDE practice since it's been incorporated back in the 60s and 70s. They're, the methods that we use today are still predominantly what were implemented back then. Radiography. There's very little change to to what we do. Maybe the sources have got a little stronger. Maybe the film has got a little better. Ultrasonic testing. Obviously, the equipment has evolved significantly, but the testing approach is pretty much the exact same as when it was initially implemented. And mag particle, in the bridge industry, I think most people are just using the dry um, dry particle yoke method. So that really hasn't been any change to that process. But what has changed is the materials that we use today. We're no longer using just 836 carbon steels. We now have high performance steels. We now have corrosion resistant steels. Some of our engineering practices has changed, right? We're no longer designing members to be riveted together in the field. We have accelerated bridge construction. So a lot has changed, but the NDE methods that we apply have not. And the primary issue is the materials that are changing. NDE is very reliant on being applied to, or one of the components of applying NDE properly is knowing the material that you're testing. So so the medical field, they have, the bridge industry really hasn't evolved much, but the medical field has, and a lot of the technologies we use, X-ray, ultrasound, the medical field is using as well, and they have evolved a lot over the years. They're now using digital imaging, sonograms and ultrasonic MRI imaging. It's much better than it was 20 years ago. So I would say probably over the last 10 to 15 years, there's been a nice progression of NDE advancement, or nice progression of trying to implement more advanced NDE practices into the highway network. So PennDOT, back in 2013, we started allowing digital radiography. That was written right into our construction specification that the fabricators or the contractors are allowed to use digital radiography. And additionally, back here in 2020, last year, when we updated our construction specification, we now allow phased array ultrasonic testing. Both of those methods require that an acceptable NDE procedure be submitted for use, submitted for review before use. So part of the review process would, excuse me, part of the review process would be to ensure that they have qualified personnel, that we can actually access the data. It doesn't do us any benefit to use these advanced NDE practices if we're not getting a data component. That's the selling point of it, the visual aids, the ability to maintain a permanent record. And we also ensure that they meet industry requirements such as ASTMs, ASNT, and AWS among few. So digital radiography, like I said, we initially started allowing it back in 2013. And that was based on the fact that a fabricator had approached us and said, "Hey, we want to use digital radiography in place of film radiography." And we entertained it. We said, "Okay, that we need to see that it's going to meet or exceed the quality of film radiography." So they went through a demonstration process, probably over a year, to prove that. Basically, what they were doing was using digital radiography on flaws that they were, or discontinuities that they were finding as they were testing with conventional radiography and doing a comparison. So we also needed to ensure that we would be able to access and review the files and archive them. So, but at the end of the day, it just made sense, right? Other industries are using it, the medical field, Department of Defense, Department of Energy. It just made sense that if they're doing it, why can't we? And looking at the medical field, I mean, it's these these radiographs are actually mine from a couple weeks ago, but or a couple months ago. I'm sorry, but the medical field radiographs are to that quality level that you can almost see muscle tissue or muscle definition, and industrial radiography is it's obviously not the same quality, but we're dealing with different materials. Steel's more dense than than muscle tissue and bone. So, but the quality is actually pretty good. So industrial radiography uses these little placards, these image quality indicators that you can see here on the right side. They have number 40 written on them, but they have different levels of sensitivity to them, different levels of sensitivity indicators to them in terms of hole size. So with conventional film radiography, it's almost unheard of to get a 1T sensitivity on a 2.5, 3 inch member. With digital radiography, we were exceeding that. It was routine that we were getting sensitivity to the 1T level. So again, it just made sense for us to allow the process. So looking at it from a archiving and standards point of view, the medical field has this DICOM standard. It's an international standard actually, but how it addresses the ability for different medical organizations to be able to access the same files. So if you, let's say for instance, if you're skiing in Colorado and you break your leg and you get an X-ray there, and then you come back home here to Pennsylvania, those X-rays are transferred to your doctor either electronically or through a CD, and they are able to access them without having to purchase any special programs. So it addresses all the metadata that has to go with the test method that's stored in the background. So industrial NDE has a similar standard. It's an ASTM standard that addresses those exact principles. So, excuse me, it addresses the need that the data be stored in commonly accepted terms, that you're able to always access the files, archiving. So right now we archive our film radiography in boxes. And with our digital radiography process, we're now archiving it online or on an electronic document management system, and we're always able to access those files just by pulling them up. That was the purpose of DICONDI, and there's no special system that we had to purchase. There's no special program that we had to purchase. I'm sorry, in order to review the files. That becomes very difficult to manage if you have four different types of radiography systems. So there's actually two different types of digital radiography. There's direct radiography and computer radiography. So direct radiography is more what you would probably see in the medical field, where you have that rigid panel, and actually that's what our fabricator is using. whereas computer radiography is very similar in nature to conventional radiography, where it's using a flexible imaging plate, and those imaging plates would capture a latent image and be sent through a scanner to extract them. So the disadvantage there is that you could only expose that imaging plate one time before you run it through the scanner. With the digital detector arrays, it's constant it's constant exposure. You expose one area, you get instantaneous results. You move down to the next one, get instantaneous results, and so forth. Nobody ever actually approached us to use computer radiography yet, but so I will focus here on direct radiography. So direct radiography uses this rigid panel. If you ever had an X-ray at a medical office, it probably look very similar. So it requires a couple things. Obviously, the computing hardware, which is the panel itself, software. So the Dicandi standard only addresses would only address the communications of the record. So whoever's doing the actual exposing of the or actually capturing the radiographs would need special software and special licenses to do that. So there is a software component for the testing party, and then imaging display. In this case, a monitor. We're getting rid of the the light boxes that we would use for conventional radiography. So so one of the components of the software, or one of the features that has to be built into the software, is a measuring tool. You obviously can't take a ruler and measure accurately on on a monitor. So this took a little bit of back and forth with the contractors, saying, what are you actually going to use to calibrate your measuring device in the in this software. So what we ultimately decided on is that it was going to be an IQI, and it was going to be placed directly on top of the digital detector array. So you don't have to deal with the geometric enlargement as much as you would with placing it on, or trying to use an IQI that's placed on top of the component. So at the same time, that same fabricator had a pretty large project for us that included some very long longitudinal web splices, and they've requested use of digital radiography without removing the weld reinforcement. There was a thought process there that because the image quality was much better than we would get with traditional radiography, that they would be able to actually perform this without removing the weld reinforcement. Like I said, it was quite a few 100 feet, I believe, of weld that they were doing at the time. And ultimately, we said, okay, you have to demonstrate that to us. And you can see here that it's still radiography. That weld reinforcement is still going to mask some of the indications. So we did not allow that process to occur. So advantages of digital radiography over film: obviously faster results, near instantaneous for direct radiography. With direct radiography, it's also doing some frame averaging that has potential to reduce exposure times, and it does for thinner components, and increased image quality over film radiography, and electronic transfer of data. So we've been transferring files through OneDrive, through FTP sites for the last 7 years. And now that we're in this situation where we're not routinely going to the office, obviously that makes it a lot easier for us. So there's no mailing of CDs, there's no mailing of flash drives, there's no physical component to it. So switching gears a little bit to phased array ultrasonic testing. So So interestingly enough, the same fabricator that requested the use of digital radiography has has now proposed using phased array ultrasonic testing in lieu of radiography. Um, so so phased array ultrasonic testing doesn't really differ that much from ultrasonic testing, the conventional ultrasonic testing. It still operates under the same physics principles. I mean, they really don't change. What we are changing is the number of piezoelectric elements that we're using and the amount of data that we're collecting. So each individual element is sending out some type of mechanical wave, and we would we end up collecting data or A scan data. A scan being your traditional ultrasonic testing output. We end up collecting A scan data at each individual test angle, and what that allows us to do is create images, 2D images, for better interpretation practices, better understanding of what those mechanical waves are interacting with. So, so we took a good long look at phased array. It's obviously it was coming. It was just a matter of time before it got accepted into some of the codes. Um, but there is some additional considerations for the application. Like I said, material properties was kind of a big one that came to light through an actual NCHRP study, and it doesn't just apply to phased array ultrasonic testing. I mean, there's like I said, we're no longer using the same materials or the same A36 steel that we were using back in the 60s and 70s when we first started allowing some of these processes. So material properties have a significant influence over the test method. So the calibration block, transducers, scan plans, joint geometry, it's all things that need to be considered before you just implement phased array ultrasonic testing. Starting with material properties. So there's this anisotropic acoustic behavior that happens with some certain steels. And it really relates to texture of the steel. You can see on the right these two microscopic images of different steels, grade 70 quenched and tempered, and a grade 70 HPS thermomechanically controlled process steel. It's been somewhat historically known that these thermomechanically controlled process steels have this anisotropic acoustic behavior to it. There's no issues with the mechanical behavior. Actually, this TMC process is used to get better mechanical properties. But throughout the globe, German shipbuilding spec here, DNV Note 7 addresses the need to consider TMCP for anisotropic behavior. So does the Japanese code and the API. And what it actually influences is the velocity, the rate at which the mechanical wave propagates through the components. So it's more significant in doing shear wave testing for weld inspections or CJP weld inspections, which was the proposal for use in lieu of radiography. So what that looks like, right? So on the left is an anisotropic material, on the right is an anisotropic material. And what that looks like is that you would have a large scattering effect, a large distortion of the wavefront, ultimately resulting in lack of signal response from a reflector. The signal to noise ratio is just not there. So it makes it very difficult when you're looking at an A scan to actually pick out any type of discontinuity. So it's something that has to be considered as part of the calibration process. It has to be considered as part of the scan plan process. What type of steel you're actually testing? What are the material properties? So, like I said, it's more significant on the shear wave process because it's the velocity is the refracted angle involves Snell's law. The velocity is a function of Snell's law, so it basically will throw off your ray tracing, or in some cases it causes a complete loss of energy at some of those higher angles. It causes mode conversion, so you actually have the ability to miss discontinuities if you don't consider this property on some of these steels. So the calibration block, so conventional ultrasonic testing would use 1018 IIW nickel-plated block with a somewhat empirical equation to calculate attenuation properties. For phased array, we are using distance amplitude corrections and time-corrected gain corrections. Basically, what that means is we have to have a calibration block that can be calibrated over the full use of that sound path. Bridge steels, we have some pretty thick members, 2.5, 3 inches, 3.5 inches, which means we're no longer carrying around a 5 to 10 pound block. We now have to produce a 70-pound block that allows the full sound path, or calibration to the full sound path. So the transducers, slightly different approach than the currently prescribed AWS method that uses a 2.25 megahertz probe, and that's been there since the 1960s. It's there for a number of reasons, right? The 2.25 allows a good penetrating energy. It allows a good wavelength for detecting certain size flaws. It allows you to easily account for some of the attenuation parameters. But phased array allows a little bit more latitude in judgment, and it's been somewhat commonly accepted throughout the different industries that a 5 megahertz probe is the one that people just fall back to. 5 megahertz with 64 elements or 32 elements. Being used to get basically the same type of, if not better, scanning. And then we're no longer doing a raster type scan. We're doing encoded line scans where instead of moving forward and backwards across the full length of the joint, we would just move parallel to the length of the joint, but the calibration process would be done manually. So you have to account for when we're actually doing a parallel scan, line scan, are we losing some of the dynamic scanning gain because we're no longer manipulating the probe side to side. So it's not currently in the code, but it's something that needs to be considered for implementation purposes. So scan plans are very important. In the past, we were applying conventional ultrasonic testing. We didn't need to know as much about the joint geometry as we do with phased array. So the joint geometry and scan plan development for sectorial scans requires that you're within plus or minus 10 degrees of the weld fusion face, and you weld fusion face to basically improve detection of discontinuities. Those are the test angles that have been somewhat researched to find fusion type flaws, a lack of fusion type flaws. So what that means is that you really won't be able to capture a full joint just by doing one scan. And traditionally we would have one radiograph. In this case, we would have multiple phased array ultrasonic testing data files that need to be evaluated. And actually it would be 4 for this particular joint because you have to do from both sides. So we did some parallel testing meaning in parallel with radiography testing. So we tried to do some type of comparison to what was radiography finding, what could phased array ultrasonic testing find, and are they somewhat comparable? The fabricator wants to use this in lieu of radiography. How well do they compare? So looking at the phased array data, like I said, there's 4 different files, 4 different scanning offsets, 4 different locations. You can see here you get the different imaging views. You get the plan view, you get the side view, you get the sectorial view, and you still get the traditional A scan output. So for this for this particular scanning index offset, it didn't find the full radiography rejected flaw, but it found part of it. And that's the purpose of doing the different scanning offsets. So looking at it from a different point of view, or different scanning offset, it did find primarily the whole indication, as well as did another index offset. So looking at the numbers a little bit, right? So how well did they actually compare? So you have to do a little bit interpretation of the 4 different phased array scanning files in this case. Where did the indication actually start? Where did it actually end? And come up with the actual length of the indication. In this case, it was all captured in that scanning file 4 index offset. And you might say to yourself, well, there's almost an 1.5 inch difference in discontinuity length between radiography and phased array. So did phased array miss a significant amount of the indication? And the answer to that is maybe not. Radiography has this inherent property of geometric expansion or geometric enlargement of indications. It's just naturally how the process works. So doing a little bit of back calculation, trying to figure out where the flaw actually started with relation to the edge of this component. With radiography, it was determined that the location the edge actually started from, or the location the indication actually started from the edge was about 3/8 of an inch. And then you go over to the phased array data, and it's pretty much the same location of where you started picking up the indication. So it probably didn't miss the full length. It probably compares pretty well to the actual radiography indication, or the actual indication without the geometric enlargement. So here's another example. So in this one, you can clearly see a 3-inch radiographic reject, but in this case, it's what you can't see that was kind of interesting. So out in the middle of this joint, there's actually a flaw that was not found with radiography, which is somewhat expectable, right? They're 2 different processes. One might find things that other ones won't. It's a well-known fact that ultrasonic testing is better at finding lack of fusion discontinuities. Looking at the data, obviously it found the radiographic 3-inch flaw to the left in that little interval, but it also found this other flaw out here in the middle of the joint that radiography just didn't pick up or couldn't find. So looking at those numbers, focusing on the one that the radiograph actually found, and we also used some conventional ultrasonic testing in this case, but looking at what the radiograph found and what the phased array did, it was very comparable in size. Maybe the indication was a little bit closer to the film in this case. It was a little bit lower in height with respect to that joint. So pretty good comparison of what they can and can't find. So ultimately, there's good potential to use phased array in lieu of radiography. There has to be some understanding, though, that they're 2 different processes. Radiography is good for some indications, and ultrasonic testing is good for others. So they're never going to be truly a one-to-one comparison, as was shown in that last example, where we were actually finding flaws with ultrasound that were not picked up with radiography. And then there's these large challenges, right? Just getting people to change current practice. How do you start implementing some of these more digital and advanced technologies where we're so used to just getting a piece of paper or getting a film? How do we go about changing our practices? And then how do we find fabricators that have the experience to do it? How do we gain that comfort level with the fabricators to have experience to do it? And obviously, one of the big needs is to consider material properties. With radiography, the anisotropic acoustic effect, doesn't play that big of a role with radiography, obviously, because it's not an acoustic process. But and then from our standpoint of view, the owners need to be able to access the files. Like I said, we really don't want to have to manage four different programs, have four different licenses to be able to access the files and archive them, and always be able to have access.
Sorry about that.
So, so a couple other things that we've looked at over the years or are looking at, some virtual assembly with some metrology type approach, some phased array with artificial intelligence, and some remote visual inspection. So, starting with virtual assembly, a few years back, we tried to do a scanning process to put some bridge elements together, and at the time it was a very difficult process. You almost need a staging area to be able to scan each individual component and have a good normal scan to bolt holes for alignment. And the technology advanced so fast, and it really didn't come to fruition. But it was one of those practices that we looked at and that we thought might be a good pilot to try. So one of the pilot projects that we have going on right now is actually an added component to the phased array ultrasonic testing, where we're looking at using some artificial intelligence. So basically, we take those four scanning files, those four data files that we collected with phased array, and we run it through this assisted data analysis program. And instead of looking at four files, this program actually merges the data together and creates one file for where suspected indications might be. So it is a assisted data analysis program. It still requires some human interpretation to say whether a defect is present there or not. But it's one of the technologies that we're currently looking at. It's a pilot ongoing right now. So it is contingent on having good quality scanning data. If your data, it's only going to work as well as the input. So if the data is not useful, it will not provide good results. So, hey, we're looking at some remote visual inspection technology. So this would be kind of your first person point of view. So it's a camera, or a headset, I should say, attached to the inspector's hard hat, and it allows us to be right there with the inspector to see what they're looking at. Allows us to aid in the inspection process. It allows us to use as a training tool, and it allows us to quickly and swiftly understand issues and resolve them. So, like you said, again, it's just one of those technologies that we're looking at. It is a pilot program as well, and it kind of falls right into this realm of ultrasonic testing. So with that, that kind of concludes the presentation. I'd be happy to take any questions if there are any.
Thank you, Nick. Great presentation. Very informative and very interesting. This actually has been the first webinar on the topic of fabrication and fabricated steel structure. So thank you for covering this topic. Now we have about 10-15 minutes for questions and answer. I'm also, right now I'm posting a link to the survey. So I just posted the link. So please take a moment to take the survey and submit your email address to receive the certificate for 1 PDH, and also provide feedback on this webinar and future webinars. So now we go over the questions. So the first question that we have here, Nick, is what are the challenges for field implementation?
So field implementation for a certain process or just general?
Just general, I guess, for phased array mostly. But and I know that your presentation is about fabrication, so
Yep.
it's
Yeah.
field implementation for existing structure, probably.
Yeah. So I would say in general the hurdles to overcome is cost, right? So that's what primarily why we're just using visual inspection and supplementing with NDE is the added cost, and it typically it requires an additional person trained in those type of methods to apply NDE. But looking at it from a phased array standpoint, phased array is very sensitive to knowing what you have there. Like I said, the joint geometry, the uh, the scan plan, and in the field we really won't be scanning any type of CJP welds, but we'd be scanning something with irregular surfaces. Is what my experience has been. But it's a good process actually for pin inspections because they have nice normal surfaces, and it allows you to capture most of the pin with one probe as opposed to swapping them out for different ones throughout the process. So, and we actually did a pilot or a demonstration project on that a few years back in one of our signature truss bridges out in the western part of our state. So again, it added cost of using the more advanced technologies. So
Thank you. The next question is, what was the sample size for comparison between phased array and radiography? Also, was A709 grade 50 considered for making a reference block?
yeah, so A709 grade 50 was all the steel that was used for the comparison portion of phased array and radiography. That was well known up front that if there was some HPS 70 going through the shop or some type of other steel that they would have to do an additional calibration block. So the sample size was fairly limited. It was it was done throughout normal fabrication operations. So anytime there was some type of radiography discontinuity, phased array would be applied to do that comparison. But the issue is we really don't have that many discontinuities that are found in our newly fabricated members. Those ones that I showed were the one-off situations, and I like to make the joke that they're actually the fabricator let their employees off for Christmas and they came back and forgot to weld because those indications were directly after the new year.
Mhm.
So so it was fairly limited. There's probably probably a good 10 to 15 indications that we actually did a good comparison on. And it was over the course of a few months. So this was one of our larger fabricators. They do produce a lot of steel or a lot of bridges, bridge girders, I should say. So,
Thank you. So the next question is, how visual inspection is tied to radiography. Can you elaborate more?
how visual inspection is tied to radiography?
Yes, that's the question.
They're really not. Visual inspection and radiography are two completely different testing approaches. Radiography is going to find internal type flaws. I can't think of any instance where you would say I visually see something I want to apply radiography.
Mhm.
It would actually maybe they're talking about that situation where we radiographed some core samples that we took out of the bridge. We did that for a very specific reason of ensuring that the crack tips were fully drilled out. Um, but even there, that's they're not a they're not a comparison visual and radiography.
Okay, thank you. The next question is, how do you determine if existing steel is anisotropic in sound? And if it is, do you have to have uh, like a calibration block?
Yes. So that's one of the ongoing issues that we're dealing with right now. So I'm leading a task group as part of the bridge welding committee, and we also got looped into a ASTM A709 or A6 as well. And the task group is really to come up with a methodology of saying, how do we, first of all, if we have anisotropic materials, how do we address it? So there's a couple different ways you could address it. That would be calibrating on a block that's similar. It would be inputting correct velocity measurements. So you'd measure the velocity and you just change it in your testing approach. Um, but how do you determine if a material is anisotropic? So that's that's also a function of measuring velocity. So anisotropic would mean that it varies in two different directions. In this case, the roll direction and transverse to roll direction. And and we're really trying to come up with a good method of saying what steels might have it, which ones might not. We actually ran to a little bit of a wall with understanding how steel is produced. That here in the states, thermomechanically controlled process is not as well defined um, as it is throughout the rest of the world. So we have a larger use of that process than what we'd like to to understand, I guess. It could be applied on a traditional as rolled steel, and be called as rolled, not thermomechanically controlled process. So it's going to take a little bit of effort to to understand what steels might be anisotropic. So it boils down to measuring velocities though and correcting for refracted angles in the testing approach. So either by using a calibration block that's similar or by being able to manipulate the velocity in the program.
Thank you. We don't have any other question in the chat pod, but I do have a question or just curious about PennDOT's experience on the use of phased array on existing structures. Can you also share your experience with the, I know you, a little bit you talked about the implementation challenges of phased array, but do you have any like ongoing project, any experience?
So we actually don't have any ongoing projects with phased array on existing structures. Like I said, we did one little pilot project out in our western districts for using phased array on bridge pins. It's just it's really being looked at right now from a bridge welding committee standpoint for looking at welds, and we really wouldn't look at welds in the field. I mean, those unless some type of fatigue damage had occurred or some type of impact damage, and it's in those situations where you have plates that are bent, deformed, to where phased array is not a good approach because you have to have good contact with the surface. So we currently don't have any pilot projects going on for in-service phased array applications.
Okay, thank you. And the last question is, do you use the same NDE tools for testing steel embedded in concrete?
For testing steel embedded in concrete. So reinforcing steel, I would assume?
Yeah, I would assume.
I can't say that we are doing that. Obviously, you can radiograph concrete and find rebar, but that's not a practice that we implement here at PennDOT.
Right. No, we don't use the same NDE tools for steel embedded in concrete. There are different technologies. Phased array obviously is for steel, radiography. You cannot do, I haven't seen any application of radiography embedded steel in concrete. So with that, I guess we are getting into the end of the webinar. Thanks so much, Nick, for sharing PennDOT's practice for NDE for fabricated steel. Many thanks to all of you for showing interest in NDE and participating in this webinar. So the next webinar will be on June 28th, which will be focused on application of NDE on pavements. You should all have a link to the meeting invite. If you don't, let me know. I can forward it to you. And just a reminder to do the survey. I appreciate your feedback, your suggestions for future webinars. There are some questions, so I appreciate your response to the survey. So with that, I'm going to adjourn the webinar and wish all of you a great week. Stay safe, everyone. Thank you.